About a minute. I've been asked by several people for a copy of the presentation. Actually, I prepared this presentation earlier, and there is a copy of it with the animations, as well as several other lectures that Dr. Menzel and I gave that are on the NSMC website. Furthermore, the presentation is being put on some type of video thing that I don't quite understand, but it's marvelous technology, so it will be available maybe for you to take the video and look at later. So there are a number of ways this is being handled. So you don't have to grab a copy out of my computer. It's already somewhere. What I want to do now is talk about if we have these boundaries, what happens to them over time? How can they maintain themselves? What role vorticity plays in this? What about new showers on them? And then what happens when these boundaries run together? And I'll recall you the earlier manned spacecraft image that we saw where these boundaries ran into each other. We had new thunderstorms forming. This is a well-formed boundary. Now you see it. That's moving away from this thunderstorm area, or the thunderstorms are moving this direction, and this boundary is being left behind. It's very slowly moving to the north. And I point this out to you again. The boundary, it has weak convection on it, so we know that the upward motion is not enough to cause a thunderstorm unless it reaches an area where there is deeper moisture and more instability. And then, at that point, it can create a thunderstorm. So we'll do our first nowcast together. Here's our first nowcast. I will tell you we've been measuring the movement of this boundary as it moves, and it's moving in this direction. And I say to you, will there be a thunderstorm here? In this clear region? Don't think so. What about in here where this convection is? Better chance, huh? Over here, less better chance. So, our very first nowcast, we got it right. Where we moved in to a convective region, we have new thunderstorms. Where we move into a clear region, we didn't. Now, why should you be careful doing this? Because this is during the daytime, and over land, you can see I've now begun to heat up in this region, and cumulus has formed. (1900, 2100), 2 hours. So over 2 hours, it's only moved a little bit. But now my nowcast for this area would have changed had I only used this image, because I didn't realize the sea breeze in here should continue to form during the day. Had I used that information, then I could say this area is all very prone to afternoon thunderstorms, although there's nothing here now. We know the sea breeze is beginning to form, and by the time the boundary gets up there, it will trigger new convection. So you can see how it's a nonlinear evolutionary process. So you can't make one forecast and walk away. You continually update and modify. So we see the boundary over time. If we look at it, the forcing along it, here the clouds are thick. This is just a time-lapse movie. We see that the cloudiness gets less and less and less. That means the vertical forcing on that boundary is decreasing over time because it's getting further and further away from the cold dome. However, where it does run into the convective area, we can still trigger deep convection locally. So here again is the idea of a mesoscale analysis. It's over a several 100-kilometer wide area. we have surface observations, and I tell you, okay, do a mesoscale analysis of this and give me a forecast. This is the way prior to satellite imagery people looked at the surface observations. They had looked at upper air several hours ago, and now you go in and you try to analyze this and tell me where thunderstorms are going to be. It's not an easy job. Because what are you really looking for? You're looking for areas of organized convergence, boundaries, things of that nature. And it's hard to do just from that until you put satellite data with it. When you put satellite data with this, some of the things begin to show up very quickly. For example, this boundary across here, you can see its precise location. And you see some of the winds that go with the thunderstorms there. But you can locate the boundary precisely. This frontal zone shows up nicely in this in an analysis, but would you put it here? Would you put it down here or right across that station? But when you come down here, you can see, aha, the front sits right there. Over here, what appears to be a confused picture is not confused at all once you put the satellite imagery with the surface observations and do your mesoscale analysis. So you can locate your boundaries. You can do very good things there. The frontal zone, right through here, very clearly shows up with the convection forming along that frontal zone. But would you have put the front back here? There's a big difference between if the front is right here versus if the front's back here. Well, no question about where it is now. So what does satellite data give you? You can look at this satellite data with enough experience and practice, and immediately you realize you're looking at a mesoscale analysis. And more than that, you're looking at mesoscale processes that are occurring. And it's those processes and how they fit together that give you new convection. And you can see the resultant convection from the top to the bottom slide where these boundaries intersect and interact. It's just beautiful. This is a 250-meter MODIS image over Florida. So again, we're seeing the effect of the process. Some process has gone on to create this MODIS image. And it's over a very small area. But we see, aha, what have we learned? Well, there's kind of a clear region in here. And it has a little cirrus cloud in that clear region. Wonder where that came from. Maybe there was an earlier shower that's created the clear zone, and this is the boundary that's left by that shower. Well, over here, maybe that's the same thing. Right in this area, thunderstorm. Probably got the sea breeze across here somewhere. Well, fortunately, we have geostationary satellite data that helps us understand this little bitty area in the MODIS image we're looking at down here. Oh, there's that thunderstorm that created that clear region and this weak outflow region. And, oh yeah, this little one right here that moved inland. Well, we can see it rains and then it becomes clear right here. Oh yeah, and there's that front. And there is rain occurring on that front, pushing it further inland up here that we see in this place. Oh, and this ring out here that just seems to appear out of nowhere. Well, this ring is from that thunderstorm and the rain cooled air. So all of a sudden, by taking the geostationary satellite data, we take the mystery out of the mesoscale. Mystery's gone. Now, the mystery is what happens next. And what happens next is the front moves all the way across Florida. It interacts with the convergence we see develop on this sea breeze front, and boom, massive convective development. Similarly, outflow boundaries from here move up to the north and interact with the front. The flow across this island, that organized flow creates thunderstorms who have boundaries. And you begin to realize very quickly that every single place you have a thunderstorm and it rains, you have a boundary that's created. Doesn't matter where. Deep tropics, that process goes on again and again and again. And it's that nonlinear interaction that causes the new thunderstorm formation. I want to show you a recent observation from Meteosat's second generation over the Sahara Desert. Now you think, well, desert, you know, we get thunderstorms out there. Sure, we get a lot of dust blowing around and whatever. But the dust that's blowing around from those thunderstorms is because you've rained into that area and evaporated, causing the dust to come up and then spread out. So the dust that's blowing away from these storms is actually an indication of the cool, moist air here that's mixed. You remember I showed you the mixed updraft region and all of that going on. This is blowing dust, sure, but it's filled with moisture. Now, here's a boundary from this thunderstorm, and this is sure out over a dry, dusty area. But the moisture from this is going to move out, and let's see what happens. So here's the dust. This pinkish area is the dust region. This dark, dark region are the thunderstorms and clouds. But watch where the new convection forms. And I think this ought to animate. Here it goes. There goes the boundary. Do you see it? Gets out over here. We got a lot of moisture here. And in that moist area, new storms begin to form. You see them form and move out. Up into here. In that moist laden air, new storms form and move out again. So you're actually seeing a process. You're seeing the transport of moisture. You're seeing something that appears chaotic, which in actuality is not chaotic at all. These boundaries are creating a lot of thunderstorms. Here we're going to come with a new set right down here. Watch that moisture move out, trigger new storms. Now the moisture is here over the night. Daytime heating comes, new storms form, and there goes some new boundaries. It's just beautiful. And it's the way convection happens. And without satellite data, this you just don't realize. I want to talk about large-scale forcing in convergence zones and organized convergence. And we're going to talk about overshooting thunderstorm tops and rainfall and things of that nature as we go through here. With this lecture, by the way, there are detailed notes with every slide. So if you care to get the lecture off the NSMC website and read about every single slide and every single movie, I've prepared those notes. So you can go back and study this in detail. One of the marvelous things that happens in the atmosphere when you have large-scale forcing is you tend to organize into narrow convergence zones between along a front or along where a squall line shall develop. In those organized convergence zone, you don't immediately get the thunderstorm, but you get the convergence zone. Then you have to go from the cumulus to the cumulus congestus to the thunderstorm stage. And you can watch that happen in the satellite imagery. These are two different views of the same storm, one from the GOES East satellite, one from the GOES West satellite. And with China now, you have two satellites viewing from different angles. And when you get very high resolution visible imagery, you'll be able to see some of these differences. I remind you again of our three-dimensional perspective of the storm and how differently it appears in one image versus another, depending on your viewing perspective. But what does appear very clearly is this organized convergence zone. Now, what are these organized convergence zones? Again, let's just go back to a regular field experiment where we looked at them. And here we're flying across this region, in here, where an organized convergence boundary exists. And you see it's developed later in the satellite imagery very nicely. And then thunderstorms. But look at what it is. It's a region of locally deeper moisture. in that convergence zone that eventually causes thunderstorm development. This is very important. Why should you have a sounder on a geostationary satellite? Well, I want to be able to follow these deeper low-level moisture boundaries and watch them develop over time. See where that really unstable area is. That's easy. Give me a hard question, not an easy one. Now, the question is, how often do I need to look? And we'll see that in a minute. Here's another organized convergence zone that we see once we get cumulus development on it. And that convergence zone actually caused large thunderstorms to form. A bigger storm here than anywhere else causes this tornado. Very, very vicious tornado. But the question is, why wasn't that storm here? Why did it have to be here? And I think the answer lies in the moisture field if we would have had it with a geostationary sounder. When we look at nowcasting, convection, and severe weather, a number of things are important, and I've listed them here. Vertical wind shear we know is important in storm development. The evolving instability field. And we know that instability field evolves over time with heating and the development of the cumulus field that will occur with it. Obvious, the strength of the storm-produced cold pool. That is, the rain-cooled air produced by that storm and its strength are important in severe weather. And we'll see why. The updraft strength is important, ample characteristics, environment interaction. These loops give us an idea of why we need to have a geostationary sounder. And what these are loops of are convective available potential energy, convective inhibition, lifted index, and total precipitable water. And you can't see a lot from these loops. You think, well, gee, you must expect me to be some kind of visual genius to be able to put all this together. But this is a loop over 3 hours of 37 images of what a satellite image might appear from a high-resolution model. Now, what I want to do is take a look at this spot right here. And this is why you need geostationary soundings. Because between the time of consecutive overpasses of a sounder in a polar orbiting satellite, your convective available potential energy at this spot went from being very high to very low. The precipitable water dropped off dramatically. The lifted index, I'm sorry you can't see that very well, but it obviously decreases as your convective inhibition increases. Another way to look at it is a point like right here. And this is the sounding as it's changing at that point. The sounding is on the right. The sounding changing at that point over a 3-hour period. And we'll watch it. It should speed up once it all loads. So, the soundings throughout this whole area are changing their structure dramatically over a 3-hour period. We already know this from some of the aircraft flights we've done. Now we're doing it, looking at it in very, very high resolution models. This is why you need geostationary sounding data, so that you can monitor these areas at very frequent intervals and see where the most instability is increasing or decreasing. We can actually, with the current polar orbiting satellites, I'm not saying don't use the polar orbiting satellite sounding data. Far from it. We should use that information as well as we can and then blend in the cloud field and its evolution with that data. That's all we have right now. But we can get very, very good temperature profiles with the current hyperspectral information from polar orbiting satellites. In fact, we can resolve inversions. So that's important. We can look at the cloud field ahead of a developing cold front, and we can see some very well organized things. Right here we see the organized convergence zone along which the storms are forming. we notice this region here is filled with cumulus clouds, and the region up here with something that appears as streets or wave clouds. This is actually very much like air that's very moist, very unstable, that's just to the north of a warm frontal zone. So we have differential heating going on across here with a warm frontal zone and moist boundary layer air, and we have a cold front here moving into this area. This air can become, is very unstable, and upon lifting you can get dramatic thunderstorm activity by realizing that moisture, but it requires a lot of energy. So here it is. Over time, we see the squall line as it develops and intense thunderstorms are occurring. Now this motion is what's known as Earth relative motion. So the Earth stands still and the clouds move. And sometimes that's good for looking at a broad scale picture, but it's very difficult for looking at a storm grow, because a storm moves very fast and you're trying to watch the storm as it moves and grows and figure out the dynamics of what is going on. However, we've made movies where we actually hold the storm still and we let the Earth move. Here you see the Earth moving. Well, that Earth is moving because the storm is not. We can do animations like that very easily. And quickly you see that the air feeding this storm is coming in from the east of the storm. That means the storm is catching up with that unstable air. And you can watch that air change character as it interacts with the storm. You see the cumulus behind it. Most of the convergence along this line is happening because that storm moves into that air. What you perhaps didn't see was this storm rains and it leaves outflow region behind right here. And that becomes important in this storm's life cycle. Here's another such storm forming. Again, you see the same thing. The storm catches up with the air ahead of it, but the low-level air moving in from the east. Very little convergence into the backside of this storm with the drier air in the cumulus field. We see large overshooting tops form. And we also see a very curious thing in the anvil spreading out to the west against the prevailing flow when the overshooting top is there. Now all of this is important in the dynamics of this thunderstorm and what's going to lead it to produce a very vicious tornado. In fact, several of the storms along this line did. So we see that the shear, low-level flow from the east, high-level flow from the west relative to this storm. Now we might ask ourselves what's going on here. We might ask ourselves about the jet stream flow coming into that storm, and we'll ask ourselves about that next. So now we hold the cirrus still and let the storm move. And what you see, very interestingly, is I call this the case of the cowardly cirrus, because as the cirrus approaches the storm, or as it looks like the storm approaches the cirrus, you see the cirrus evaporate and back away. See it actually decelerate? Now, what's going on here is a fairly complicated process, but it's very important in the life cycle of the storm. You can also see outflow boundaries produced by these storms. I'll go up to the previous slide and see if I can animate it so you see it again. The storms rain, you can see the boundaries they produce of the rain-cooled air they're leaving behind. That's very important in the storm's dynamic. But what's happening here is as the updraft develops and we take this high momentum air aloft, we hit the tropopause and we create a dome of high pressure. And that causes the air to spread out in the anvil. And it is such a strong updraft and such a strong high pressure region up here that this air actually spreads out against the prevailing flow. And relative to the storm, in this area where we see the cirrus come in and appear to slow down and back up, we've got a high pressure region right here, a dynamic pressure. It's a dynamic pressure that is created by the storm and the interaction with its environment at upper levels. Now, what does that dynamic pressure do? it diverts the upper level wind flow around the storm. And actually the wind around this side of the storm, or the south side, may go much faster than around the north side, which could, if you accelerate air through this area, when you accelerate air at one level, what happens? With the acceleration of air, you lower pressure. You recall Bernoulli's equation, perhaps. P1 plus V squared over 2, P1 plus V1 squared over 2 is equal to P2 plus V2 squared over 2 at that same level. And you can work those things in your own way to say, well, if I make this velocity go to 0, what happens, what pressure field exists? But also, if I cause the air to go faster here, what does that do to the pressure field? Lowering the pressure is certainly helpful in storm development. This is just another example of this 30-minute or 30-second and 1-minute interval satellite data. Notice the long plumes downwind from the anvil. Now, in a few slides, we're going to get to the dynamics of thunderstorms themselves and how they produce tornadoes. Again, let's talk about convergence or vorticity on the local scale. Convergence on pre-existing vorticity. So if I've got an outflow boundary, right, we know we've got this vorticity in that vertical plane. So if I've got this rotation in this vertical plane, and I have another thunderstorm come along and hit that boundary, it's going to take the rotation here and push it up into the storm. So I take rotation in this vertical plane and I can put it into the horizontal plane of this thunderstorm's updraft, and suddenly I'm causing that thunderstorm to rotate. And we know rotating storms are ones that help produce tornadoes. So that's tilting a vorticity from one plane into another. Now, where did that vorticity come from? It came from the differential heating that caused that outflow boundary. So the rain process caused the outflow boundary that then interacted with the storm and caused the rotation. Here we have a case of a boundary across here. We have wave clouds up here, a warm front, warm sector here. So this area is one where cool air is here, warm air is here. So you get this vertical rotation in this vertical plane. A thunderstorm forms and moves down that boundary. As it moves down that boundary, it begins to feed on the vorticity in here and begin to rotate, and you can even see the hook echo in this storm and in the storm right behind it as it went down that boundary. The updraft, a very intense updraft with this is infrared imagery of that, and the blue is colder, a very cold updraft with a V-shaped blue region that we've come to associate with very intense storms. And there's still a little controversy and research going on with this, but we know that that is one signature of these storms. I've got my own thoughts on that. If there's time, I can tell you about it. This is an example of some severe storms with hail and tornadoes and what they look like. And I'll go over each case very quickly. This was a boundary south of Chicago. As this storm formed and moved on that boundary, it produced a large tornado in this area. And it's the vorticity along that boundary that was important. Here's another boundary. A storm forms, moves across that boundary, tornado. Here's a squall line and a warm front. And the storms that formed on this squall line began to intersect with that warm front, and we had a tornado here. And then as the squall line interacted further south, there was tornadoes here, and further south, tornadoes here. So when storms move into vorticity-rich environments, whether it's a warm front or a boundary from another storm, and they have intense updrafts, they can begin to rotate, they can begin to take advantage of that vorticity and produce thunderstorms and severe weather. Here's just one other case. This boundary right here was created by earlier thunderstorm activity. A large thunderstorm formed with a low pressure center here, and it moved right across this boundary and produced a number of devastating tornadoes right along that boundary. Same thing here. Thunderstorm formed over south of Lake Michigan, moved down to the south and left a boundary here. This storm formed, moved right down that boundary, and you had a path of severe weather and tornadoes. So again, concentrating a very strong updraft into that very localized vorticity region is where you get the tornado activity for one class of tornadoes. So you can see the circulation within the boundary interacts with the updraft of the storm, and you take this circulation and you put it into that updraft, and suddenly you have a very strongly cyclonically rotating updraft. And why is it put into that updraft? Because the outflow from this storm takes it and tilts it up into that area. So that's your tilting mechanism at the very local level. Now, this is another one of our images of 1 minute interval satellite data. And again, it helps us get a good conceptual model of a severe storm. And let's talk about what we said before, and we see it happening right here. Here's the anvil spreading back against the prevailing flow. So there's absolutely no reason for this part of the anvil to be back here. I mean, the upper level wind would love to push it this way. Something has pushed it back there. And that's the strength of that updraft, so we're slowing this air down. We also create a new boundary layer in here with the rain-cooled air produced by that storm. And that storm then moves down this way with its updraft. The downdraft from this storm, the rain-cooled air, we see part of it here, and part of that, comes around that way, right in here. And that's forcing new air up right down here. See that air feeding into it? As the cumulus field shows us that air feeding into it, see it feed in? Creating this monster of a storm. Well, let's see what happens conceptually. The storm rains, leaves a boundary behind. Okay, I agree to that. The anvil spreads out against the prevailing flow. It's mid-level dry air coming in here. The high pressure region up in this area forces this air to accelerate this way and also to sink with the cold dome. While the thunderstorm itself forms, so it's leaving a cold dome, you can see how relative to the storm, it's actually causing its own little mini occlusion. Because I'm leaving this pool of cold air behind. And that actually can interact with the rain-cooled air that's being produced out in front of the storm. So I've got a rain-cooled region here, but I've got this little pocket of cool air back here, and we see it happening. Look at that. You can absolutely see this occluding itself in that area. So I'm tilting my own vorticity up into the updraft of this supercell, causing it to rotate and giving me a very long lifetime in tornado activity produced here. So a storm that is strong enough, leaving its own boundary behind and interacting with the environment, can feed on its own vorticity due to its rain-cooled air and produce a tornado. Now this is shown very clearly right here. You can see the updraft towers going up into this large thunderstorm. A little later, you see those towers have left a rain-cooled region behind. You can actually see the occlusion right in here, feeding off the vorticity in this region. And the tornado we got out of this storm was over 1 mile wide, which you see right here. So it looks like this. So we have a nice viewing perspective where we're looking at the boundary, the towers of the storm feeding up into the overshooting top, and right in here we have the tornado. So again, the processes that are going on due to the rain-cooled air from these storms and how they create their own environment and interact are exceptionally important. There have been a number of studies on looking at the difference between daytime and nighttime convection, and basically daytime convection occurs with heating and organization along a convergence zone, whereas nighttime convection occurs during the evening, and it's elevated. That is, it's above an inversion layer because an inversion forms and moisture moves to the north. We'll take a look at that very quickly. This is a satellite image, and it's during the I'm going to stop it right here. This is an infrared image during the daytime. And along this region right here, that line where you see dark versus lighter, this is moist air during daytime. This is drier air out over a desert. And these are thunderstorms up here that are in colors. And so what you see during the daytime is the moist region does not heat up near as dramatically as the drier region, and that's why it's showing as cooler here. As we move into nighttime, you see what appears to be the reverse of that process, if I can stop it at the right time, where suddenly you're cooler over the drier region and you're warmer over the moist. And we know this. I mean, that over deserts and you get huge temperature excursions day to night. Over moist regions you don't. But what we're actually seeing is a formation of inversions in these regions. And once the inversion forms, you begin to see the moisture begin to move very rapidly in this direction. Well, it's moving in that direction. It's also moving up in this direction and helping feed these nighttime thunderstorms. So if we can identify areas where inversions are forming in this moist region, we get a better idea of where low-level jets may form and help feed nocturnal thunderstorm activity. And we can actually do that now with the hyperspectral sounding data that we have. This is in the infrared window region, and there's moisture contamination within that region. And over here on the left is temperature. So temperature is higher at the top and lower at the bottom. So right in here, we see the surface temperature, this blue line, and if we look above that surface temperature, the moisture is getting warmer with height, which is a low-level inversion. But if we look at this region, we see a very hot surface, and the moisture is cooler with height, which is daytime, and it's a very unstable atmosphere. So actually, with these new hyperspectral sensors, we can monitor the destabilization of the atmosphere or the stabilization and see where we're going to form inversions or faster destabilizing. And this is very important for nowcasting, because if we know where the inversions are and we can watch them decrease, we know that there's less convective inhibition and we can get strong convection forming. Or if at nighttime we see inversions forming like this, then we know in this region we can form low-level jets and have a very fast northward transport, or a very fast transport of moisture, if we have the right synoptic situation to form a low-level jet. A very quick thing on cloud top structure and overshooting tops, because we've been through a number of things in this short little 2-hour lecture. But we know these tops are a reflection of air coming up from the boundary layer and causing the thunderstorms. The anvil spreads out and takes on a characteristic temperature of the environment, or the stable layer where it spreads out. That can often be at the tropopause. And then you have air that can overshoot that region and become much cooler. Now you can see this process here in this sounding. The red line is the atmospheric sounding. Excuse me a second. In here, we brought air up from the boundary layer. Where's my little pointer? bring air into the boundary layer, get condensation, release of latent heat, vertical motion. All of this positive energy, we get to this level, and this is where we have our maximum vertical motion if there's no mixing. And that maximum vertical motion will cause that air to overshoot into the tropopause and become much cooler. I'm fine, thank you. That's okay. And overshoot. And so we realize this cold temperature. But that cold temperature is not in equilibrium up here, so it must sink down. And this process continues, and we get these very strong overshooting tops where we have a strong thunderstorm. So what does the overshooting top tell me? By the temperature of that overshooting top, if I know something about the instability in the environment, if I'm up here, I know I had to have a certain vertical motion right at this level to get to that cold temperature. And if I know that, then I can say something about the intensity of the storm. But I can't say anything about the intensity of that storm unless I know something about the structure of the tropopause into which that air is overshooting. I know that when I come up here, I must continue to rise moist adiabatically. But I don't know how strongly I have to push up against a tropopause. Okay? So that's a missing link. But by and large, I know that I can get this very strong overshooting. So when I see storms that have very strong overshooting tops, and they last for a long time, what this is telling me is there's got to be some organization with that storm to allow that to happen. Otherwise, the storm would develop and die. So there's some organizing mechanism keeping that storm in being. And by watching these storms with these strong overshooting tops that have long lifetimes, then I know I have a storm that's got organization. It's the storms with organization that cause weather to happen, intense weather. The other thing that I have to be very careful of is the resolution of the satellite imagery I'm looking at that overshooting with, because our current geostationary satellites may show a cloud top that is only 3 or 4 degrees colder than its anvil, whereas with higher resolution polar orbiting satellites we can see it may be 15 degrees colder. So you must understand that. We have things going on at cloud top that we can see in different spectral bands. Spectral bands and their application was a different part of this talk. I will just say with the 3.9 micron channel imagery and some of the 1.6 micron channel imagery and near infrared imagery, we're able to see differences in ice crystal structure above cloud top. This is from MSG, and here we have a series of thunderstorms. You can see they're overshooting tops. If we look in the infrared data, we see V notches, or this cold overshooting top with this V characteristic, which we know is indicative of severe storms. However, if we look at the 1.6 and 3.9 micron channels where we can get an idea about reflection in ice crystal size, we see that on the storm to the right, this storm, we have smaller ice crystals above the anvil. And we believe those smaller ice crystals are due to a more undiluted ascent in that storm, and it's spewing them out at the top of the updraft. So this storm, even though they both appear to be the same, we think has a more organized updraft and might be the one you would expect to be more severe than the one over here. So multispectral data can help us with that. Rainfall, basically they're infrared techniques that look at longevity of storms, overshooting cold areas, again, this is like vorticity, integrate over time. If I've got a very cold area but it's moving very quickly, it can't rain a whole lot over an area. But if I can continue to have that cold top area over a certain region, then I can get very intense rain. There are microwave techniques, there are blended techniques. I would really point this out to you that a number of people around the world do rainfall estimation, and they have products that are available on the web that I'd point you to for rainfall. This is a difference. This is a hurricane that produced intense rainfall, and again, the different techniques all showed the heavy rainfall in the same area, so there is consistency there. I always feel like there's got to be a poor man's method of doing rainfall estimation, so I developed one in a system called Ramsdes, which was just a simple average of sequential geostationary satellite images in the infrared. So you just take the IR temperature and you continue to average it together over about a 2-hour period. And I don't have the movie to this, but you can see this region right here stands out. And it's where I had continuous cold areas when I averaged my infrared data together. I also had a little bitty area down here that might have a little rain. This had a lot of rain, a lot of heavy rain over the same area because the cold tops were very, very persistent. So you can do a very simple averaging technique to find out where there's heavier rain. There are a number of web-based products. I'll point you to the virtual lab. That Professor Hsu and others can tell you how you can get to the virtual lab. You can actually get to it through the WMO Space Program website, but they've changed the interface to the WMO page, so it's a little more difficult to get to it, but that is certainly one place. You can go onto the internet and search for virtual lab, and actually you'll find it and be able to go into that, and you can see a number of products. There's an International Precipitation Working Group. That International Precipitation Working Group links to the virtual lab, but it also links to a number of different types of rainfall techniques. So go onto the web and search for International Precipitation Working Group, and you can go to their website. I'm not going to talk about climatologies very much, but here I think one thing you can see show up very clearly. I don't have to tell anyone what part of the world we're in, but notice this is during the month of May. Its averages over about a 6-hour period for the whole month of May, so it's the May 1st through the 31st at 01, 02, 03, and whatever Greenwich Mean Time. I point this out to you in this type average. Can you find the mountains? It's not very hard, is it? You can see they are places where convection is just preferred. Do you see the intertropical convergence zone, the subtropical ridge, the convergence boundary that generally likes to exist in this area? Do you see the two mountain ranges actually that are across Taiwan? One here, one here. You see the mountain area down through here, over here. I don't know this terrain as well as many of you do, but certainly, again, this points out the importance of differential heating, sea breeze, so forth, and you can develop climatologies like this to help you do better nowcasting and understand better where convection will form under various regimes. With that, this is just another type thing over Australia where you can see the sea breeze over time and the convection up through parts of this area and over this mountain. So there are a number of ways to look at convection. With satellite data, it becomes much more enjoyable and a whole lot more fun because you can now, I hope, after this long lecture, and I appreciate your patience with it, I hope you have a better feeling of the use of satellite data to understand and nowcast convection. Convection happens in a very well-ordered process, and satellite data can show you that process. Thank you very much.